NENOMATICA, where mathematics meets YouTube excellence. Welcome to this mathematical video where we will prove an inequality. The problem asks us to prove the inequality shown on screen. We need to prove that 1 plus 1 over root 2 plus 1 over root 3 plus dots plus 1 over root n is greater than 2 times the quantity root n plus 1 minus 1. Let's start by focusing on the right side of the inequality. We have 2 times the quantity square root of n plus 1 minus 1. We'll manipulate this expression to make it easier to compare with the left side. We can rewrite it as 2 times the quantity square root of n plus 1 minus square root of n multiplied by square root of n plus 1 plus square root of north divided by square root of n plus 1 plus square root of n. This manipulation is based on multiplying the numerator and denominator by the conjugate of the expression. Now, let's simplify this expression. In the numerator, we have 2 times the quantity square root of n plus 1 minus square root of north times the quantity square root of n plus 1 plus square root of n. When we multiply these terms, we get 2 times the quantity n plus 1 minus n. This simplifies to 2 times 1, which is just 2. So now our expression becomes 2 divided by the quantity square root of n plus 1 plus square root of n. Now, let's establish a chain of inequalities. We have 2 divided by the quantity square root of n plus 1 plus square root of n. This is less than or equal to 2 divided by the quantity square root of north plus square root of n, which equals 2 divided by 2 times square root of n, which equals 1 divided by square root of n. Therefore, we have established that 2 times the quantity square root of n plus 1 minus 1 is less than 1 divided by square root of n. Now, let's connect this back to our original expression. We can multiply both sides of our inequality by the square root of n plus 1 minus square root of north divided by the square root of n plus 1 minus square root of n. This gives us 2 times the quantity square root of n plus 1 minus square root of north divided by square root of n plus 1 plus square root of north times the quantity square root of n plus 1 minus square root of n is less than 1 divided by square root of n. Let's simplify the left side. We have 2 times the quantity square root of n plus 1 minus square root of n divided by the quantity square root of n plus 1 plus square root of north times the quantity square root of n plus 1 minus square root of n. The denominator simplifies to the quantity square root of n plus 1 squared minus the quantity square root of n squared, which is n plus 1 minus n, which is just 1. So our expression simplifies to 2 times the quantity square root of n plus 1 minus square root of n is less than 1 divided by square root of n. Now, let's invert the inequality. If 2 times the quantity square root of n plus 1 minus square root of n is less than 1 divided by square root of n, then 1 divided by square root of n is greater than 2 times the quantity square root of n plus 1 minus square root of n. Let's start by looking at the problem. We need to prove the inequality 1 over the square root of n is greater than 2 times open bracket the square root of n plus 1 minus the square root of n close bracket. Our approach is to verify the inequality for specific values of n, and then use induction to prove it for all values. Let's start with n equals 1. Now, let's test for n equals 2. If n equals 2, then 1 over the square root of 2 should be greater than 2 times the square root of 3 minus the square root of 2. Let's continue by testing for n equals 3. We substitute n equals 3 into our inequality. And finally, let's write the general case. If n equals n, then we get our original inequality. Now, we'll combine the sides of the inequalities we've developed. We have 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of n is greater than 2 times open bracket square root of 2 minus 1 close bracket plus 2 times open bracket square root of 3 minus square root of 2 close bracket plus 2 times open bracket square root of 4 minus square root of 3 close bracket. We can rewrite the right side of the inequality to simplify it. We get 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of n is greater than 2 times the square root of 2 minus 2 plus 2 times the square root of 3 minus 2 times the square root of 2 plus 2 times the square root of 4 minus 2 times the square root of 3, and so on. Notice that the right side forms a telescoping series where many terms cancel out. The final result is 2 times the square root of n plus 1 minus 2. Therefore, we've shown that 1 plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over the square root of n is greater than 2 times open bracket the square root of n plus 1 minus 1 close bracket. In summary, we've proven the inequality by first testing specific cases for n equals 1, 2, and 3. Then we combined these inequalities and simplified the resulting telescoping series to arrive at our final result. This proof technique is a powerful approach to establishing inequalities involving sequences and series. Welcome to our math video. Today we'll solve an inequality proof step by step. Let's begin by understanding what we need to prove. Let's look at our example. We need to prove the following inequality: square root of n minus k plus square root of n plus k is less than square root of n minus m plus square root of n plus m, where 0 is less than m, which is less than k, which is less than n. Let's start our proof. We'll begin by restating our problem. We need to prove that square root of n minus k plus square root of n plus k is less than square root of n minus m plus square root of n plus m, given that 0 is less than m, which is less than k, which is less than n. Now, our first step in the proof is to rearrange the terms. We'll move the square root of n minus m to the left side and the square root of n minus k to the right side. This gives us square root of n plus k minus square root of n minus m is less than square root of n plus m minus square root of n minus k. Next, we'll multiply both sides by the same expression to simplify. We multiply both sides by the expression, the quantity square root of n plus k plus square root of n minus m, all over the same quantity square root of n plus k plus square root of n minus m. This equals 1, so it doesn't change the inequality. Now we can apply the difference of squares formula. Remember, a squared minus b squared equals a plus b times a minus b. So the left side simplifies to n plus k minus n minus m, all divided by square root of n plus k plus square root of n minus m. Let's simplify the numerators on both sides. On the left, n plus k minus n minus m simplifies to k plus m. Similarly, on the right, n plus m minus n minus k simplifies to m plus k. Notice that both sides have the same numerator, k plus m, or equivalently, m plus k. Since both numerators are the same, we can rewrite this as an inequality of reciprocals. Taking the reciprocal and flipping the inequality sign, we get square root of n plus k plus square root of n minus m over k plus m is greater than square root of n plus m plus square root of n minus k over m plus k. Now, let's simplify by noting that k plus m equals m plus k, so our denominators are equal. This means we can directly compare the numerators. So we have square root of n plus k plus square root of n minus m is greater than square root of n plus m plus square root of n minus k. Let's stop and think about what we found. We started with the inequality square root of n minus k plus square root of n plus k is less than square root of n minus m plus square root of n plus m. But after our algebraic manipulations, we've ended up with the opposite inequality. This means we found a contradiction, and our original assumption must be incorrect. Let's look at why we got this result. The key is in our given condition. We know that k is greater than m. This means that square root of n plus k is greater than square root of n plus m, because k is greater than m. And square root of n minus m is greater than square root of n minus k, because k is greater than m. Therefore, the original inequality is actually reversed, as we proved. Therefore, we've proved that the inequality is actually square root of n minus k plus square root of n plus k is greater than square root of n minus m plus square root of n plus m, when 0 is less than m, which is less than k, which is less than n. This proves our inequality, which completes our proof. Welcome to this math video, where we'll prove an inequality involving an infinite series. Let's start with our problem statement. Let's begin by analyzing each term in our series. We'll establish inequalities for each term separately. First, let's look at 1 over 4. We can write this as 1 over 2 squared, which is less than 1 over 1 times 2. Similarly, for 1 over 9, we can express it as 1 over 3 squared, which is less than 1 over 2 times 3. Continuing this pattern, for the general term 1 over n squared, we can write it as 1 over n times n, which is less than 1 over n minus 1 times n. Now, let's add up all these inequalities. On the left side, we have our original sum, 1 over 4 plus 1 over 9 plus 1 over n squared. And on the right side, we get 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over n minus 1 times n. The right-hand side can be simplified using partial fractions. Let's look at each term. Let's use partial fraction decomposition to simplify each term on the right-hand side. For 1 over 1 times 2, we can rewrite it as 2 minus 1 over 2, which equals 1 over 2 minus 1 over 1. Similarly, 1 over 2 times 3 can be written as 3 minus 2 over 2 times 3, which equals 1 over 2 minus 1 over 3. And generally, 1 over n minus 1 times n equals n minus 1 over n minus 1 times n, which is 1 over n minus 1 over n. Do you see the pattern? Each term can be written as the difference of two fractions. Now, let's substitute these simplified forms back into our sum. The right-hand side becomes 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3, and so on, plus 1 over n minus 1 over n. This is a telescoping series where many terms cancel out. When we add these up, all the intermediate terms cancel out, and we're left with 1 over 1 minus 1 over n. Let's simplify further. 1 over 1 is just 1, so our inequality becomes 1 over 4 plus 1 over 9 plus 1 over n squared is less than 1 minus 1 over n. Since n is greater than 1, the term 1 over n is positive. This means 1 minus 1 over n is less than 1. Therefore, we've proven that 1 over 4 plus 1 over 9 plus 1 over n squared is less than 1, which was our original inequality to prove. Welcome to this math video where we'll work through a beautiful proof from mathematical analysis. We'll prove that for any natural number n greater than 0, the following inequality holds: 1 over n plus 1 plus 1 over n plus 2 plus 1 over 2n is greater than 1/2. Let's break down our approach for this proof. We'll apply direct comparison between each term in the left-hand sum and corresponding terms on the right. This will lead us to our conclusion. Let's start by examining the first term. If n is greater than 1, then 1 over n plus 1 is greater than 1 over 2n. For example, if n equals 3, we have 1 over 4 is approximately 0.25, which is greater than 1 over 6 or 0.16. Similarly, for the second term, if n is greater than 2, then 1 over n plus 2 is greater than 1 over 2n. We can actually prove these inequalities algebraically. For the first one, we need to show that 2n is greater than n plus 1, which is true when n is greater than 1. For the second inequality, we need to show that 2n is greater than n plus 2, which is true when n is greater than 2. We can continue this pattern. We observe that for each term in our sum, as long as n is sufficiently large compared to the index of the term, we have that 1 over n plus k is greater than 1 over 2n. This pattern continues until we reach the last term, where 1 over n plus n, which equals 1 over 2n, is equal to 1 over 2n. Now, let's sum up all these terms. On the left side, we have 1 over n plus 1 over n plus 2 plus 1 over 2n. On the right side, we have 1 over 2n plus 1 over 2n plus 1 over 2n with n terms total. The sum on the right simplifies to n times 1 over 2n, which equals 1/2. Therefore, we've shown that 1 over n plus 1 over n plus 2 plus 1 over 2n is greater than 1/2. This completes our proof of the original inequality. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.